Hi everybody, today's lesson is about inductors and this is the last part of electromagnetism. Now this is a new component that is being introduced at year 13, so you haven't come across this term inductors before, but you have come across something very similar to inductors, and that is in the past you've come across resistors and you've come across solenoids. Now resistors are just wires which heat up or convert electrical energy to heat energy. That's what you've learned, right? And that's what slows the current down. So that's what resistors do. Solenoids are coils of wires that also have current going through them. Now the thing that you've learned about solenoids is that, or any piece of wire, whenever there's a current going through a wire, there is a magnetic field or flux around the wire. And you've also learned that in a solenoid, which is a coil of wire, I had a coil, this is as close to a solenoid as I can get, okay? A coil of wire through which there's a current going has a magnetic field, and in the solenoid it has a uniform magnetic field, right? Okay, and we've learned this before. Now, an inductor is very similar. The only difference is that the inductor has got many thousands of turns of wire. So when you have an inductor in a circuit, so I'm just going to draw a DC circuit. So we're looking at inductors in DC circuits, because later on we're going to be looking at inductors in AC circuits when we learn the last part of electricity. But today let's see what happens. So if you have a source and you have, let's say, lots of turns of wire, which is an inductor, and you have a lamp and there's a switch. Now when you close the switch or at switch on, so closing the switch or switch on completes the circuit. When the circuit is complete, for an instant of time, current, this is the positive end, current is going to go through the inductor coils and there. So there's an increasing current for a moment in time. And when there's an increasing current, there is an increasing magnetic flux. Now, whenever there is changing flux, you know that there's always an induced voltage that's produced to oppose this change. So within the inductor coil itself, there's going to be set up an opposing voltage, and this opposing voltage is known by many names. It's called the back EMF. It's also called the back voltage. It's also called the induced voltage. It's just many names for the same thing. The symbol for this could be V for induced voltage, or it could be the EMF sign. So you might find one of these two in them. The thing is, what happens is that this back voltage actually opposes the increasing current. So a lamp in the circuit which has an inductor in it is going to take a little more time to reach full brightness, because the inductor, the back voltage, is slowing the current down. Okay, and at the same thing, when you open the switch, or what happens is the current is going to go from a maximum while the current was flowing, and when you stop the current flowing by opening the switch, the current is going to fall to zero. But if there's an inductor in the circuit, it's going to again oppose this change, because there's going to be a changing flux due to the changing current, and the lamp will just fade off slowly. It doesn't just go off immediately, it just gets dimmer and then it fades off. Now in the computer animation that I've put up, that animation, the computerized one, just didn't work for switch off. It works only for switch on, but this is what actually happens at switch off. Okay, so this property of the inductor, where there is a changing, when there's a changing flux and it has this induced voltage, this is called inductance. And the symbol for inductance is L, and the symbol for an inductor in a circuit, is kind of like coils of wires, is like this. Okay, and in order to make an inductor more efficient, it often has an iron core, and the line underneath just says it's an iron core. In reality, inductors are made of wires, and wires have got resistance. So the symbol for an inductor in a circuit, it's often given like this, with the L representing the inductor and R is the resistance of the inductor, okay, because of the wires, right? And now the thing is, this flux is the amount of flux is proportional to the size of the current. So bigger the current, greater the flux, okay? So flux is proportional to current, and the constant of this proportionality is equal to Li, where L is the inductance, and this inductance is measured in Henry. Okay, this is called self-inductance. Your M for transformers was mutual inductance. So this is really self-inductance because it's happening within the same coil itself. Now, the size of the induced voltage is given by the rate of change of flux. So the size of the induced voltage could be this, or it could be the V is equal to rate of change of flux, how quickly flux changes with a negative sign. And instead of writing phi, we can write Li. So the inductance times change in current over change in time gives you the size of the induced voltage. So this inductance is actually a constant for any particular coil. It depends on how many turns, what material is it made from, and does it have an iron core, is the core solid, is it powdered, and so on. Okay, so this was just an introduction to inductors. I'm going to make a couple more short videos with a little more about what happens with inductors. Okay, so bye for now.